Good afternoon, professors. I'm Him, and my project name is on Hilbert function and positive definite quadratic forms. And so the theorem now comes. We let a function kx, which is the summation of ak x to the power k, with k equal to 0 to infinity, and ak greater than 0 for all k. And this function has a radius of convergence r. And we take alpha 1, alpha 2 to alpha n are in the range of negative roots of r to roots of r, and they are all pairwise distinct. Then the quadratic form, we let the quadratic form P.K x1 x2 to xn equal to the summation of k alpha I alpha j xi xj, with I and j equal to 1 to n, is positive definite. And the proof first comes is we observe the function k alpha I alpha j, which is the summation of ak alpha I alpha j to the power k, and can be rewritten as summation of roots of ak alpha I to the power k times roots of ak alpha j to the power k. And now we denote W as the L2 space, which is a set of sequence AI, which are real and square summable, which means the summation of AI square converge. And this L2 space has an inner product AI BI equal the sequence equal to the summation of product of AI and BI with I equal to 1 to infinity. And now we define a function phi with range negative roots of R and roots of R to the L2 space by sending x to the sequence roots of A0, roots of A1x to roots of AK x to the power k and to infinity. And we note that the summation of roots of AK alpha I to the power k square is indeed k alpha I square, and this converge. Since alpha I square are in the range of negative R and positive R, so we now rewrite k alpha I alpha j, which is summation of AK alpha I alpha j to the power k, to the inner product form, which is phi alpha I times phi alpha j. And we consider the quadratic form QK x1 x2 to xn, which is equal to the summation of k alpha I alpha j xi xj. And our goal is to prove that this quadratic form is positive definite. So we consider its associate matrix, the quadratic form's associate matrix, which we call AK as k alpha 1 square, k alpha 1 alpha 2 to k alpha n square. And the function k can be written as the inner product phi alpha 1 to phi alpha n the inner product. And since AK is in an inner product form, which means all its entries are inner products, so we can conclude that AK is positive semi-definite. And now it remains to show that the matrix AK is invertible. And we have to claim that AK is invertible, which is equivalent to proving that phi alpha 1, phi alpha 2 to phi alpha n are all linearly independent in the L2 space. And now we suppose some real number lambda 1, lambda 2 to lambda n then we have lambda 1 phi alpha 1 plus lambda 2 phi alpha 2 plus 2 lambda n phi alpha n are all equal to 0. So by expanding the left hand side, we can get root of A0 summation of lambda I with I equal to 1 to n, and roots of A1 summation of lambda I alpha I to roots of AK summation of lambda I alpha I to the power k are all equal to 0. And we equating the first m term, since A0, A1 to an minus 1 are all not equal to 0 as the hypothesis stated. So we can eliminate the roots of A term and get a system of equation which is 1, 1, alpha 1 to alpha n, alpha 1 squared to alpha 1n minus 1, and alpha n to power n minus 1 times lambda 1, lambda 2 to lambda n are equals to 0. And the matrix left hand side is known to have a determinant which is the product of alpha j minus alpha I with all I smaller than j, and this is random Moore matrix, and this determinant isn't equal to 0 by the hypothesis that alpha I isn't equal to alpha j. So therefore the system has only trivial solution, which is lambda 1 equal to lambda 2 equal to lambda n are all equal to 0. Therefore, phi alpha 1 to phi alpha n are all linearly independent, and we are done with the proof. And apart from this, besides the main theorem, I also proved some variants of it, and which is instead of enforcing all the coefficient AI to be positive, we can have some of them to be zeros. And more precisely, the theorem is that we let kx be summation of akx to the power k equal to 0 to infinity, which is Taylor's expansion, with ak greater than or equal to 0, such that the set hk, which k is positive integer, and ak greater than 0, this set has a positive upper density. And also with some restrictions, which is alpha I isn't equal to 0 for all I, and the absolute value of alpha I isn't equal to that of alpha j for all I isn't equal to j. Then the quadratic form Q_k x1 to xn, which is summation of k alpha I alpha j xi xj, is positive definite. And this is a variant of the main result that I have also proved. Thank you. Thank you.